So oftentimes we are looking at reference data. We're looking at standard states just because it makes things simpler. So we started out with this equation here, the relationship between delta G, delta H, and delta S, and that is applicable under any conditions. But we're going to focus our analyses on standard state thermodynamics. And so what standard state means is that pressure of any gaseous players are at 1 atmosphere of pressure, and any solutions have concentrations of 1 molar. And furthermore, reactions do kind of need to be happening under constant temperature. If you think about combustion reactions, that's maybe not realistic, but lots of reactions can happen under constant temperature. So when I say there's reference data to look to for some of these values, I'm talking about big tables like this one. This is just a screenshot from a PDF of standard thermodynamic values. And so what we have on a table like this, and you'll probably need to consult tables like this for maybe homework problems, and I've provided a PDF of this on Brightspace. But what you're looking at here is the entropy values. You should be feeling pretty good about that, defined that in the last lesson. Often these entropy values are given in joules per mole Kelvin, which we'll think about later on. We sometimes need to do some conversions between joules and kilojoules. We also see the enthalpy of formation, so just a little recap on that. If I'm looking at the enthalpy of formation of aluminum oxide, for example, that's the enthalpy change that occurs when forming the compound from the elements in their standard states. So aluminum, oxygen in the form of O2, kind of the most common form, those react very exothermically to create that aluminum oxide. Because aluminum by itself is an element, it has an enthalpy of formation of 0. And you'll also see on here standard free energies of formations. And so these are, in a way, similar to enthalpy of formation in terms of how it's defined as forming a compound from the elements in their pure and most common forms. So yeah, it follows that, if the substance, like aluminum oxide, for example, has some intrinsic entropy and this enthalpy of formation value, that you could kind of combine those terms according to that G equals H minus temperature times entropy. So yeah, we can use that free energy of formation data in a very similar way as to how we calculated the entropy change of the reaction in the last lesson. So we can also define free energy of reaction as the sum of the free energies of formations of the products minus the sum of the free energy of formation of the reactants. So this is this equation is very much equivalent to the other delta G reaction equation, delta H minus temperature times delta S. And which one you use depends on the available data. So the next 2 videos are actually going to be examples using both of these methods, both of these equations. And last smaller point, I mentioned that a lot of that data is at 25 degrees Celsius. You can apply that standard free energy of reaction equation to other temperatures, but you just kind of need to know what you're dealing with. The temperature does need to be constant over the course of the reaction. And to get the best results, you would want temperature-specific enthalpy and entropy data. However, usually those changes in entropy values, for example, are pretty small over small temperature ranges. So this equation is pretty commonly applied at temperatures other than 298 Kelvin or 25 degrees Celsius. We can estimate the delta G of the reaction at other temperatures, and we do that by using the standard state data that's probably taken at 25 degrees C or 298 K, but inputting the actual temperature that this reaction is happening at. So yeah, our practice on this is actually going to be going back to that same acrylonitrile reaction from the last lesson. What I'll be doing on paper is calculating the free energy change of the reaction using enthalpy and entropy data, and then also going back and doing it a second time using the middle column here, the free energy of formation.
All right, welcome to lesson 2.2. What I'm looking at right now on this paper is the work I did in lesson 1.3, where I solved for the reaction entropy for this kind of complicated reaction that synthesizes acrylonitrile, one of the products over here. Just to recap what we did, we looked up the entropies of all the reactants and products, and I listed them right under the reactants and products in the equation, which I kind of like to do. It's a little atypical, but that's how I like to sort of write my problems. And then really all I did was sum up the product entropies. Oops. So by multiplying each individual entropy by the coefficient and just adding them all together. And so even though this equation looks kind of complicated, I'm really just taking that sum of the product entropies and subtracting the sum of the reactant entropies. And so what I found was the reaction entropy was minus 686, and that shows that entropy is decreasing. So moving right along, the slide at the end of the last video gave me also the enthalpy and free energy data for the reactants and products in this system. And I mentioned that there's really two approaches to determining the same value, the free energy of the reaction. I can either take my enthalpy and entropy data, or I can use the standard free energies of formation. So we're going to go through both approaches. So for approach number 1 here, I already have my entropy of reaction. I calculated that before, and it came out to be minus 686 joules per mole Kelvin. The temperature was given to me in the problem as 298 Kelvin. And so that means the last thing I have to solve for to be able to solve for delta G is the enthalpy of reaction. Approaches just like what we saw with the entropy. The standard state enthalpy of reaction is also the kind of sum of the products enthalpies of formations minus the sum of the reactants. And again, taking all the coefficients and multiplying them by the enthalpies of formation at standard state for all the reactants. So even though I have my values for enthalpy and free energy in this nice list, I just often tend to make mistakes when setting up this calculation. So I'm going to go ahead and write them right under each of the individual reactants and products. So I'm starting out with the enthalpies to calculate the enthalpy of reaction. And important to note that these enthalpies of formation are in kilojoules per mole. So 20 minus 46, 0, 173, and 286. So yeah, like last time, I'm going to take the products, 2 times 173, and I'm going to sum them all together, plus 6 times minus 286. And that gives me minus 1370. On the reactant side, just have to remember to write my coefficients. You can also write them like, right below right below the reactant or product. But I kind of like to rewrite them. So here I've got 2 times 20 plus 2 times negative 46. And then oxygen has an enthalpy of formation of 0 because it is an element. So I'll write plus 0 just to show that I accounted for it. And that gives me minus 52. And so now I've got my sum of the products and my sum of the reactants. So our enthalpy of formation, our enthalpy of reaction for this particular reaction is going to be our sum of the products, minus 1370, minus the sum of the reactants. So this ends up giving me negative 1,318 kilojoules per mole. The units come from the original units that were on all of those enthalpies of formation. So now I have enough to solve for my delta G value as standard state. It's my delta H minus temperature times delta S. And these are also at standard state. And also, I usually try to write the reaction subscript just so it's clear what this delta is referring to, but you often see it without a subscript of reaction or RXN. So now I have to be a little bit careful here. My enthalpy of reaction is in kilojoules per mole. My temperature is in Kelvin. And my entropy change on the reaction that I solved for earlier is minus 686 joules per mole Kelvin. And since I'm going to end up subtracting these terms, my kelvins will cancel out when I multiply them, the temperature and the entropy, but I need to get these joules and kilojoules reconciled. The value for delta G is probably going to be fairly large, so I think it usually makes sense to express it in kilojoules per mole. So I can also express that entropy as minus 0.686 kilojoules per mole Kelvin. So I'm just moving the decimal place 3 spots to the left. So now to substitute in, I've got minus 1,318 kilojoules per mole minus 298K times negative 0.686 kilojoules per mole Kelvin. And so those kelvins will cancel. And that's going to give me minus 1318 plus 204, I'm rounding here, but that's all right, kilojoules per mole, which gives me finally 1,114, negative 1,114 kilojoules per mole. So that's my free energy of this reaction. And the fact that it's negative tells us that it's spontaneous. You always want to make that assessment, and I usually go ahead and write it down right away.